Hello, this video is about integration by parts. Specifically, this is about the integration by parts formula and where it comes from. There will be other videos where I show you how to use the formula, but in this one we're just trying to give you some intuition for the formula itself and why we're able to use it. And let me first state the formula and then we'll talk about it a little bit. This is the formula. The integral of u dv turns out to be equal to uv minus the integral of v du. We're going to use this a lot. Turns out if u substitution doesn't work, and our basic rules don't work, and our 9 techniques for rewriting integrands don't work, frequently the next thing we do is try integration by parts. Now, in practice, basically what this is allowing us to do is it's allowing us to take an integral that's complicated, one that we can't evaluate using any of the previous rules, and rewrite it like this. So we're going to be able to write it as a function minus a different integral. And our hope is that this integral will be simpler than the integral we started with, so that through doing integration by parts, this is something that we can solve using either basic rules or u substitution, or perhaps even integration by parts again. But before we practice using it, I just wanted to show you where it comes from. Now, this is just a review, or maybe something that you've never known. U substitution was something we talked about at the end of Calc 1, and that is the chain rule in reverse. So if I had to use the chain rule to take the derivative, if I want to undo that to get the function back, I'm going to have to use U substitution to take the antiderivative. Integration by parts is similar, except it's not the chain rule in reverse, it's the product rule in reverse. So it's going to allow us to undo the product rule. You might remember that the product rule resulted in 2 terms, and we'll review that in just a second. Integration by parts is going to allow us to take the antiderivative of one of those terms. That's where we're going, and I just want you to know if this video is confusing for you at all. Of course, I would be happy to try to make you a clearer video, but if it is confusing, you don't actually need to know where this formula comes from to be able to use it. But I do want to show you where the formula comes from for those people who are interested, and for those people who don't want to just simply apply a formula and not understand its derivation. So that's where we're going. We're going to derive this formula for integration by parts now. There are 2 facts that we need in order to do that. First, you need to recall the definition of the differential. The differential of y is defined this way. If y is equal to f of x, the differential of y is defined, or is notated dy, and it's given by f prime of x times dx. So you're just going to take the derivative of your y and multiply by dx. So here's an example, or here are a couple of examples. If I have y equals x cubed, dy is the derivative of x cubed, so that's 3x squared by the power rule. Remember, we bring the power down and multiply by x to the 1 less power, times dx. That's the definition. We can think of this as a rearrangement of dy over dx equals f prime of x, but technically that's not exactly what it is. So we're just going to define it this way. So here's another simple example of a differential. If y equals sine of x, dy is cosine of x dx. You're probably most comfortable seeing a differential in a u substitution problem. So let's say u turned out to be e to the 3x. That function was nested inside of another function. Well, the differential of u, du, is just the derivative of that. Derivative of e to some power is e to that power times the derivative of the inside times dx. So these are just examples of this idea, this definition. If y is equal to f of x, then y prime is, or dy, the differential of y. So that's how we read that. Or you could just say dy is equal to f prime of x dx. It's just the derivative multiplied by dx. Dy is not the derivative. Dy is the derivative times dx. So keep that in mind. So we need that definition of the differential in order to derive this formula. We also need to remember the product rule. Now there are lots of different ways to state the product rule. If you used prime notation back in Calc 1, you probably saw it written this way. The derivative of f times g, or fg quantity prime, is derivative of the first times the second plus derivative of the second times the first. And I like to write it out in words for my students because this is how I think through it. So it's the derivative of the first times the second, and I'm going to emphasize that that second function is undifferentiated. Don't do anything to it, just write it down. Plus the derivative of the second times the first. And that's also undifferentiated. So this is one way of writing it. We could also use Leibniz notation. Because of the form of integration by parts, instead of using f and g, I'm going to use functions u and v. So I'm going to let u be a function of x, and I'm just going to call it u of x. That's not u times x. That's u as a function of x, just like we're used to seeing f of x, as where f is a function of x. U is a function of x here, and v is also a function of x. And I'm going to call it v of x. Using Leibniz notation, I've got this. Now, this is an operator. If you're unfamiliar with this notation, you should know d dx means take the derivative with respect to x of whatever is in these brackets. I'll always use brackets. Some people will also use parentheses. This is take the derivative with respect to x of whatever is right here. So this is the derivative with respect to x of u times v, where u is a function of x and v is a function of x. So this is my first function, and this one's my second function. So we're doing exactly the same thing here. Here that we did here. We're just using slightly different notation. Up here we used f and g, and we used prime notation. Down here we're using u and v, and we're using Leibniz notation, or d dx notation, or you can think of it as operator notation for the derivative. Now, according to our product rule, the derivative is derivative of the first times the second. Derivative of the first is du dx, using Leibniz notation, times the second. And then we're going to add the derivative of the second times the first. So that's my product rule. Now, if I take this entire equation and I multiply it by d dx, or not d dx, excuse me, I'm so sorry. Multiply the entire equation by dx. I'm going to get this equation in a different form. Now, because of what I'm about to do, because I'm about to use the differential, I'm going to change the order of each of these products. You know that 2 times 3 is the same as 3 times 2, right? We can multiply in any order we want. So if I've got this times this, I could flip those. That'd be totally legal. I'm not changing anything. Multiplication is commutative, so that's totally fine. So I'm just going to write the derivative second instead of first. So I've got this derivative equals derivative of the first times the second plus derivative of the second times the first. And I'm going to take the whole equation and multiply it by d dx. I keep saying that. I'm going to multiply it by dx. Okay. Now, by definition of the differential, that is the differential of u times v. And this is, what's the derivative of u with respect to x times dx? That's the differential of u. And this part is the differential of v. You can already start to see the parts of the integration by parts formula. We've got the differential of u times v is v du plus u dv. All right. Now, if I just take the antiderivative of both sides, remember you can take the antiderivative term by term. So if I've got a sum of 2 terms over here, the integral of the sum is the sum of the integrals. So I can just apply that integral to each part. Then according to according to the product rule and the fact that all of these statements are equivalent, I've got this. This statement is true. Now, this first one is actually u times v. And it might be a little bit easier to see if I actually wrote it in this alternate notation. This differential of u times v is the derivative with respect to x of u times v times dx. I'm just writing the other stuff down. So basically I've got the antiderivative of the derivative. These guys are going to undo each other and we're just going to be left with u times v. Because the antiderivative and the derivative undo each other. And we're almost there. Integration by parts says, look at this guy by itself. I'm going to subtract this term from both sides and then rearrange the equation so that this is on the left instead of the right. So this is equivalent to the integral of u dv equals uv minus the integral of v du. And that's our formula. It's basically just the product rule in reverse. And in the next video, I'll show you how to use the formula.